Hello everyone, my name is Viraj, and today we'll be looking at the ninth problem from the CP31 sheet by TLE eliminators under the 900 rated questions. Let's go. So moved on to my 900 over here and went to the ninth problem, permutation swap. Alright, let's read this. You are given an unsorted permutation P1, P2 and so on till Pn. To sort this permutation, you choose a constant k where k is greater than equal to 1 and do some operations on the permutation. In one operation, you choose basically two integers I and j where these constraints are followed. J, I1 is less than equal to j, less than equal to I, less than equal to n, basically two different integers that we're talking about. And I minus j is k. So because I is greater than j, I minus j should be k. And then you swap p of I and p of j. Now what are they asking is, what is the maximum value of k that you can choose to sort this given permutation? Sort means from beginning to end, it has simply an increasing order. Alright, so we'll generalize the problem and see better. They have actually defined a permutation also to you over here, so you can read it well and understand what's a permutation. Let's generalize this problem quickly and get a hold of what are they asking. Okay, so we start off with, first of all, the first word being permutation. So comes to mind, what is a permutation, right? Permutation actually is implied from basically an n-sized array. So we call an n-sized array to be a permutation. Let's say I have n numbers in that permutation, like I have an array A. Now I'll call this n-sized array, let's say n was 5, a permutation of 5 size if all the numbers from 1 to 5 come in this and they come exactly once. So I don't need to bother about the order. So maybe if the array looks like 2, 3, 1, 4, 5, this is a permutation. So I can understand that all the numbers from 1 to 5 are coming in this. They're coming in any order, but they're coming exactly once. So this array A can be termed as a 5 size permutation. Similarly, if this would have looked like 3, 2, 4, 5, 1, something like this is also a permutation because it follows 1 to 5 numbers, all numbers are there and they are exactly ones. Order does not matter to us. So basically we can understand that any array which has 1 to n numbers can be called an n size permutation if every number falls exactly once in that array. Alright, so what you have done over here is quickly drawn a 5-sized array. Now, the argument is this array right now is not sorted, right? If I would want to state a sorted permutation or a sorted array in this case, it would look like 1, 2, 3, 4, 5. Our target is we want to make this array look like 1, 2, 3, 4, 5 or basically look like 1 to n numbers sorted order. To do that, we have been given an operation. Operation states that before starting everything, you select some value k being greater than equal to 1. Once you do that, you follow these operations. You basically pick up some index I and some index j and you pick them up in such a manner that their difference is k value. As in, let's say you pick up, let's say k was in this case, let's say 2. So I could have picked up, let's say, if these indexes are 1 based, 1, 2, 3, 4, 5, then maybe I can pick up I equals to 4 and j equals to 2. I know that 4 minus 2 basically gives me a 2 value, which is k. So now my argument is, after I have chosen some k value for myself, I will do an operation such like I choose I and j, their difference is k, and then I swap the numbers kept at p of I, or in this case, if I have the array name as a of I and a of j. So for example, in this case, assuming I would have chosen I equals to 2, sorry, not I equals to 2, I equals to 4 and j equals to 2, then I would be swapping the number that is kept at a of 2 and a of 4, which means once I do this or perform this operation, basically I would undergo a change which would make the array look like this. So 3 and 4, these numbers will swap and this becomes 4, this becomes 3. So you can say that the array has modified. Yes, that's very obvious. And what the idea over here is, since we want our target to look like this, as in we want all the numbers to be sorted, question is, what is the maximum k you could have selected for which you would have been able to finally sort a permutation? So in this, like the example that we took, I'm not arguing that k equals to 2 is the maximum. Maybe some other better k was visible. Let's actually look at some test case and argue better. Let's say we have 3, 4, 1 and 2. Okay, so idea is we want to max k. All right, we want the max k. So let's take an example. This is 3, 4, 1 and 2 and I have the 1 based indexing, so just like 1, 2, 3 and 4, simple. Now the argument is maximum k that I can take is actually 2. So I'll write over here k becomes 2. Now I'll try to just show you a quick demonstration of how k equals to 2 is working. If you take k equals to 2, you can take some first operation basically. You can take a first operation that looks like I equals to 4, j equals to 2. You know their differences are basically 2, and you swap these two numbers. So kept at index 2, index 4, if you swap, this becomes 2, this becomes 4. Next time you do a second operation that is basically going to be performed on I equals to 3 and j equals to 1. Now their differences are again 2, swap. So numbers kept at index 3, index 1 gets swapped. This becomes 1, this becomes 3. Don't you think the array has sorted itself? Of course. So you have a sorted permutation now, alright? And you did some finite number of operations. It's not required that we print exactly how many number of operations were we required to do. Were they more? Were they less? Did we minimize them, maximize them? That's not the question. The question is, what is that maximum k for which you felt you would be able to sort this permutation, allowed these operations only, or allowed pattern of these operations only, taking some ij with the difference k and swapping. Alright, so this is the idea. Now argument over here is the maximum k that we can actually take is 2. You will also find that as an answer to this case. We'll again argue, of course, later in the problem, why is this true and how did I get max to be k equals to 2? Why am I arguing not anything better than that will work, etc, etc. All right, great. So I think the problem is clear, right? We're just trying to find this max k, and I think the test case is also clear. You can take 2 minutes and basically try to see all the other cases once for yourself. Maybe try to find some pattern in that. Pause the video, try it on your own, and then let's start with actually discussing the first and most important thing, that is the expected time complexity in this problem. All right. So I know that 1 second basically will allow me 10 power 8 elementary operations. All right. And in this problem, it's very clear that one test allows me 1 second. So if I write the time or the number of operations, sorry, for every test, that is 10 power 8. Now, in a test, there are some test cases that is given by this variable t, which is 10 power 4. So ideally, I should be picturizing the number of operations I can perform for every test case. But there is a very neat statement given over here, that is sum of n over all test cases don't exceed a limit of 2 into 10 raised to 5 order, which means now I'm not bothered with all the test cases in general. Rather, for a single test file, I can compare my overall n, that is 10 power 5 order, with that particular factor. Basically, that means that now n being given in 10 power 5 order maximum, I can say that I'm trying to compare. So not exactly with 10 power 5, you can say 2 into 10 power 5, right? Because that's the maximum all summation of n that can go for every test. And I can try to get an expected idea out of this with comparison to this 10 power 8, that is for one test file. All right, so I can say that if I have a 2 into 10 is to 5 order, of course, I can create something that looks like O of n. Maybe I can create anything above that, O of n log n, that also works. If I go in n square order, that's a problem for me, right? N square won't work. So n square limits are not allowed. Anything below that is fine. N log n, n, so forth. And anything below than that, up to constant, is all good to go. So now I have an expected time complexity in my head. I'm looking for solutions that are not n square. It's basically O of n, best optimized case, or you create something like an n log n maximum. That's the max you can go. That's like an upper bound you can go, nothing above that. And this is what is going to help me create further ideas. I would not now think in directions which might help or which might actually tend to create ideas that are n square or above. I want to remain below that. All right, so this is expected time complexity. Let us now deep dive into the main key idea in the problem. Now, the key idea in this problem is very simple. All right, since we don't want a brute solution, that is what we discussed recently only, we are trying to take our focus on, let's say, a single number. All right, what we'll say is, okay, let's say you're talking about a general number pi. Okay, I have an example. Let's say the permutation looks like 3, 2, 1, 4, and 5. So let's just talk about this guy over here, that is this number 3. Now this number 3 is of course sad. Why is it sad? Because this number 3 is not placed correctly. This number 3 right now is at index 1. Of course it wants to go to index 3. To be specific, if you observe, once you actually sort the permutation and you observe at the indexes below that permutation, don't you think that basically every number is below an index which is equal to that value? One number is below one index, two number is below two index, three number is below three index, four number is below four index, five number is below five index. So right now, can I not argue that this 3 number is a sad guy because this number is at the index 1, but actually it wants to go to an index which is itself. So I am saying that right now, whatever number is there, it is kept at, let's say, the p of, let's say, index a. Then the index that is right now, that is A index, it wants to go from there to an index B, which is actually equal to this value, that is P of A. Yes, that is correct. Now, to understand this more better, can I say now, if it is at the index A and it wants to go to a new index B, which is actually that number itself, 3 wants to be under the third index, can I not generalize this and simply say that from index A to going to the index B, basically the difference of A minus B, and if I take like an absolute difference of A minus B, this should be, you can say, should be divisible by K. Whatever K that we choose, whatever K that actually satisfies everything, this difference has to be divisible, right? And this should make sense. Now, assuming, right, we have already proved that this index B is actually the number itself, that is P of A, we can even generalize it better and say A minus P of A mod, or mod doesn't matter. So to look neater, P of A minus A mod has to be divisible by K, or mod K has to be equal to 0. This has to be satisfied in order to make sure that now the number that is right now at some index A lands up being at some other number, sorry, at some other index that is actually the index B, which is actually the index it wants to go to, made sure by choosing a K which was actually like a factor of this difference. Hence, you now are capable to do the swaps and actually make a movement and try to shift P of A, so on and so forth, to the index that is it wants to go, the index B, or basically that number itself. Let's take a very simple idea. Okay, let's say I have something that looks like, let's say 7, 1, 2, 5, 4, 3, and 6. Okay, now let's just bother ourselves with this 7 guy. Of course, this number is sad. It's at the index 1. It wants to go to the index 7. What's the difference? The difference between these two indexes are, of course, 6, right? 7 minus 1 is 6. So if you choose a k equals to 6, that's fine because you can directly swap these two locations, right? Or if you, let's say, choose a k equals to 3 value, which remember 3 is a multiple of 6, then also that's going to work, because for 7 you can do 2 swaps now. You can maybe do a swap that is, so this is index 1, 2, 3, 4, 5, and 6. So you can do first a swap that actually takes you between 1 and 4 index, and then 4 and 7 index. That's also fine, great to go. And you know that 7 will land up at the last location. So don't you think that k equals to 6 also works, k equals to 3 also works? Or indirectly, if the difference was 6, that is from where or which index it is at, that is A, where does it want to go? The index B, or basically that value itself, that is P of A. If I find a k that is divisible of this difference, then that k is good to go. Great. So I think this is pretty much clear, right? You can draw some cases of your own and understand this simple fact. It's simple observation. Now that I have quoted this statement and this statement makes sense, we of course know that if this is true and it's general, then any A that I put for this particular equation has to be true, which means automatically P1 minus 1 also wants to be divisible by K, right? So mod K has to be equal to 0, right? P2 minus 2, or right, or I think the mod difference is what I should write over here, right? Mod, let's say, also wants to be divisible by K, and so forth. Pn minus n also wants to be, mod of that also wants to be divisible by K, which means that if everything of these sort of equations have to be true, and remember, what's the question? You have to find the max K. Then let's try to just rephrase this whole idea. We want to find actually the greatest divisor of all these numbers, all right? All these numbers, Pn minus 1 mod, P2 minus 2 mod, and so forth. So what's this definition actually? It's basically GCD, all right? It's no brainer right now that what we are trying to look for is GCD. So all I want to do now, or all our idea that would remain now, is run a quick loop, and for every PA minus A mod value, just keep on taking GCD, GCD, GCD with some initial value. So we can take our, let's say, G value, that's the GCD of, let's say, P1 minus 1 mod, right? And then we can keep on taking GCD of this G value. So G can become GCD of G, comma, P of A minus A, and we can start A greater than equal to 2. Again, this is a one-base indexing. So this is going to basically get us the GCD value of all these numbers, the greatest common divisor that is there for all these numbers, and that is what our answer is. All right, so let us actually run this whole idea. Why is this working on some test cases? And that's going to be very neat. Let's look at some very harsh test case. Let's just say I'm going to take, let's say test case this is 1 5 3 4 2 6. Okay, so 1 5 3 4 2 6. So let's just quickly ideate over here. This is index 1, index 2, index 3, index 4, index 5, index 6. What are the differences? I'll write this with red. Differences over here is 0, difference over there is 3, difference over here is 0, difference over here is 0, difference over here is 3, difference over here is 0. If you take the GCD of these values, don't you think you get 3? Yes, GCD of 0, 3, 0, 0, 3, 0. You get a GCD that's 3. And don't you think that's the answer? Go back. Yes, that's the answer. So you know this is working, right? And why is this working? Because if you would have simulated this in your head, basically these numbers don't need any hampering because they are already placed at the right locations, right? The numbers that would need hampering are this and this. If you just select these two numbers and swap them with a k equals to 3 value, you know that this becomes 5, this becomes 2, voila, you're good to go. 1, 2, 3, 4, 5, 6, you have a sorted permutation. All right, run this idea on some other case also. Let's just say, let's take this case. So general purpose 1, 6, 7, 4, 9, 2. So I'll copy this down quickly. You have 1, 6, 7, 4, 9, and then I think we have 2, 3, 8, 5. 2, 3, 8, 5. All right. So let's quickly write the indexes. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. And then what do you think is the differences in this? This is 0, this is 4, this is 4, this is 0, this is 4, this is 4, this is 4, this is 0, this is 4. So let's just take the GCD of all the values again, all these differences. We find 4. And yeah, that works because 4 is the answer. And that would mean that yes, in our simulation, in our head, these places would not have any botheration, any hampering because they're already at the right places. The places that need botheration can be these ones, right? And if you select a k equals to 4, simulate this, you will be able to sort. A quick simulation I can show you. You can maybe take 9 over here first, 5 comes over here. So this becomes 5, this becomes 9. And then maybe you can take 2 and 3 one time over here, 6 comes over here, 7 comes over here. So basically you create 1, 2, 3, 4, 5, 6, 7, 8, and 9. Right? And this is what we wanted. So I hope the problem is clear, right? It definitely requires some observation. Try running this idea on all the cases. They have quite a good number of cases over here to make sure that you understand what is our GCD observation over here. And once you get that, I know this problem is going to be very, very easy. All right. So now what you can do is look at the code part now and quickly wrap this problem. We have this test case t that we take as a variable. Then this n variable, simple enough. And then we take the array input. Now, this is where our main idea starts with. We have this k value, right? That's the thing that we want to print. So initially that's absolute of a0 minus a1, right? Where we start off with, and then we start off with the index is 1. Now we go and say k becomes every time GCD of k comma absolute of ai minus, and then we want a 1 base indexing. So we do I plus 1 because we started with the index 1. Now starting with the index 1 over here meant you have already covered index 0, which means you already did 0 base indexing, but we want to compare with 1 base numbers, that is 1, 2, 3, 4, 5 and so forth. So we need I plus 1. So we take the difference of ai and I plus 1, and that absolute difference is compared with k, get a GCD, k updates itself every time, and at the very end k gets printed. That is the correct answer. So this definitely runs for all the cases over here and it's going to get you an accepted on the platform also. Great. Now what is the time complexity? N order over here to take the input, right? And n order over here to take the for looping, but inside that we actually have this GCD sort of an STL function that is getting called, and that GCD function takes a log factor of what's the maximum of the GCDs that you pass. So on a very general average way, what we can say is we can say that because n is going in 10 power 5 order and permutation numbers are also in 10 power 5 order, so we can take this to be log base 2 of 10 power 5 order, right? Maximum, that is what is going to go. So we can say our time complexity has actually turned to be O of n log n, right? N log n, because n being max 10 power 5, let's say So you have n also as 10 power 5, and then every number was also, let's say, in like maximum you have 10 power 5 number going, highest number that can go. So worst case, this took a GCD with 10 power 5 order of a number. So this is n log n. Now if I plug in n to be 10 power 5 in this, so this basically it's 10 power 5 into, this is going to be something like 17 18 iterations, right? I can take a rough of 20 iterations, and this is going to give me a sort of a 10 power 6 order, right? And this is going to work. Why? Because as we discussed in the expected time complexity, we could have run n log n, and we wanted something that's less than 10 power 8. So this is good to go. And what about space? Space is again O of n only, that is dependent only on the size of the array. So that is O of 10 raised to 5 order, which is simply definitely feasible in our whole idea. All right, so an acute observation of this GCD thing was very, very important, right? Where is the number? Where does it want to go? If you build that general idea because of the idea that we don't want brute solutions, this becomes a very, very easy problem. All right, so I hope you like the video. Thank you for watching.